Hey guys, welcome to another lecture from Introductory Statistics. Today I'm going to work on a special property associated to the geometric distribution, which is called the memoryless property. In order to understand this property, let's pick up an experiment. Suppose the experiment is of tossing a coin again and again. So when you toss a coin again and again, a fair coin, you will get either tail or head, right? So X is a number of flips that you need in order to get the first head. This is the random variable which will follow geometric distribution, right? Something that we already know of. Let's consider the probability of heads to be P. So automatically probability of tail would become 1 minus P. Now, suppose that the first K trials or the flips have resulted in tail. Now, if we ask ourselves a question after these K attempts, we ask ourselves a question that how many more attempts will we need in order to get the first head? In order to understand the memoryless property, just imagine. So, suppose that we already have tossed this coin K number of times, and in all these K attempts, we got a tail. So, suppose we have K flips and all these K flips are tails. Then you ask yourself a question. How many more attempts will we need in order to get the first head? Suppose this is a new random variable, y. How many more flips until the first head? Now, just imagine. In real, if you imagine the situation, do you think there would be any connection of the next few attempts that I take in order to get my first heads? Will that be associated to the previous K number of tails that you've already had? Well, in this kind of situation, no. There won't be any impact of the previous tails that we've already attempted, we already know of. That will not have any impact on the number of trials that I will need, on the number of flips that I would need in order to get my first head from now on. That is where the memoryless property sweeps in. This, in fact, is the memoryless property, wherein in this situation, the past will not have any impact from now on. If I start looking from now on, the past will have no impact. This is not going to happen in every case. It's a special case which happens with geometric random variable. In other words, it does not matter when you start to count or what the past history is. It will not matter how many tails I've already had. If I start counting from now on, how many number of flips will I take in order to get my first head? So this scenario, more formally, will look like the following. Any random variable is said to be memoryless if what happens? For any n m greater than or equal to 0, the probability that your random variable, say x, is greater than n plus m condition to x already you know is greater than m, turns out to be just same as the probability x is greater than n. It doesn't matter what has happened. It doesn't matter how many tails you already had. So suppose, you've had m number of trials already and you know that all of them were tails. What is the probability that you will take n more trials in order to get your first head? This is what it will be equal to. It will be basically the probability that x, that is the number of trials, number of flips of coin, in order to get the first head to be greater than n. because it doesn't matter. The past does not matter. Now, why will this happen in case of geometric random variable? Why will this equality happen? Is something that I would like to prove with you guys. And in order to prove this, you need to know what is the probability mass function for geometric, what is the cumulative distribution function for geometric random variable. So let's consider the left-hand side, that is the probability, conditional probability, x greater than n plus m. Condition to x greater than m. Okay, now this is a conditional probability. Conditional probability, we all know, is the intersection, that is, probability x is greater than n plus m, and you already have that x is greater than m. Whole thing upon the condition which is probability x is greater than m. Okay? Now, what will this intersection be? This is nothing but the intersection greater than n plus m. So suppose this is m and this is n plus m, m plus n. So what is the intersection of greater than m and greater than n plus m? What is the common area? What is the intersection? Well, it will be probability x greater than n plus m. Whole thing upon probability x greater than m. Now you need to know what is probability in case of geometric. So this basically means, so in the numerator basically you have that probability x is greater than n plus m, which means the number of trials you need in order to get the first head is greater than, strictly greater than n plus m. That means you will have n plus m failures and then success. Failure means getting a tail. So this would mean probability of tail n plus m number of times, that is 1 minus p into p plus, because it's greater than. So you start with n plus m failures, then, going ahead infinitely many times. 1 minus p n plus m plus 1. So you're getting n plus m plus 1 failures, and then you get the first head. And so on and so forth like this. In the numerator, instead of n plus m, it is m. So you get tails m number of times, and then you get heads. Similarly, here you get, it's strictly greater than m. So m plus 1 number of times you get tail, and then you get heads, and so on and so forth. So what you get here? 1 minus p to the power n minus m comes out common, and p also comes out common. In the denominator, 1 minus p to the power m and p comes out common. In the numerator, now what are you left with? You are left with 1 minus p, 1 plus 1 minus p plus 1 minus p square, plus so on and so forth. Similarly, here also you are left with 1 plus 1 minus p plus 1 minus p square, and so on and so forth. Actually, this all cancels out. And hence what you get, this p also cancels out. And here you see you have the same base, 1 minus p, power n minus m, okay, n plus m, sorry, n plus m, and here minus m, because it's in the denominator. So what you get is 1 minus p to the power n. Now I would want you could have directly, I have actually solved this once again with you, but you could have directly, what you could have done is, you need to know what is the CDF. CDF for the geometric random variable is 1 minus q to the power n. So wherein we take probability x is less than or equal to n if I'm taking, or probability if I'm taking 1 minus q to the power n is same as saying 1 minus p to the power n. If you take n as the value for the random variable x, if you take x in place of n, you can just write down n x. Now, if you observe, that means what is this? If probability x is less than or equal to n is 1 minus this expression, that means this expression is probability x is greater than n. And that's what was our RHS. That's what we are saying. We're saying why geometric is actually memoryless, because see, everything cancels out as you can see here, and what you get is just the probability x is greater than n. Now, x is greater than n. What is that equal to? The probability x is greater than n plus m. Condition 2, x is greater than m is equal to probability x is greater than n. इसको सिंपल भाषा में अगर हम समझें, the probability that you take, say 13 attempts in order to get your first head, given that you have already had 6 attempts, do you think it matters that you've already had 6 attempts and you've got tail for all those 6 attempts? Well, it doesn't matter. You start counting from the 7th as your first trial, and this should be equal to, this conditional probability is simply probability greater than 7. आप क्या कह रहे हो? आप कह रहे हो कि what is the probability that I'll take 13, more than 13 tosses, given मैं already 6 tosses कर चुकी हूँ और उसमें सब में failure आया, यानी tail आया, in order to get my first head. अब अगर 6 ट्रायल्स में ऑलरेडी कर चुकी हूँ, तो दैट मीन्स मैं 7th वाले से काउंटिंग शुरू कर सकती हूँ ना. सो एट दैट जंक्शन, इफ यू आस्क योरसेल्फ व्हाट इज द प्रोबेबिलिटी दैट आई विल take more than 13 attempts in order to get my first heads, will be same as asking yourself what is the probability of getting the first head in more than 7 attempts, because this 13 is nothing but 6 plus 7. Now you can think in terms of M and N. I hope this logic is clear to you. It's a very, very logical property, memoryless, but there's only one discrete random variable which follows it, and that's the geometric one. And now you know why. Thank you very much. I hope this helps.